All right, so we started section 9.5 on Thursday, and we said this section's only the ratio and the root test. So remember, the ratio test was testing for absolute convergence, so we had to take the absolute value of everything, and we were simply looking at the ratio of the next term over the previous term. And in a similar way, we said if that ratio works out to be bigger than 1, right, then we know that the series is growing and it's going to diverge. If we saw that it was less than 1, we saw that the series was, the terms were going towards 0, and we saw that the series would converge absolutely. If it equaled 1, remember, it was an inconclusive test and you had to run something else. So the root test also tests for absolute convergence, so there will be another absolute value involved, and it's a little bit different the way we perform it, but it's actually not too bad. And what's nice is the ratio and the root come to the same conclusion. So you're going to see if the limit's less than 1, we converge. If the limit's greater than 1, we diverge. And if it equals 1, we're going to have to do something different. So for the root test, all right, first we need a series. And what you're going to look for here is a bunch of stuff raised to the n. So it could be a combination of things. So we could see like 3 to the n times n to the n divided by like 4 halves to the n, right? So you're going to see a bunch of stuff raised to the n. But we know that if you have a bunch of different terms raised to the same power, if we're multiplying or dividing, we're allowed to combine them into one thing. So just like with the ratio test, we may want to rewrite the series to make the test easier to perform. So the first thing we say was our series converges if the limit as n goes to infinity of the nth root of the absolute value of our term, right, is less than 1. So what we're going to do here is we're going to take the absolute value just like we did, so that will eliminate any negative 1s or anything that's going on. And remember, we want this stuff to be all raised to the n. So then when you take the nth root, it wipes out the exponent. Now, some of the series I looked at the other day, we had like stuff raised to the 2n, all right? So what you would have to do if you had something raised to the 2n is you would say, well, if I have 4, right, raised to the 2n, we would rewrite it as 4 squared raised to the n, because you're only allowed to take the nth root. You can't take the 2nth root. So remember, we want to make sure we got our rules of exponents down, so we could rewrite that as 16 to the n, and then if we took the nth root, we would just get 16, okay? The series is going to diverge, right, if this limit is greater than 1. And it's going to be inconclusive if the limit as n goes to infinity equals 1. So here we have to try another test. So let's look at an example of how to perform this test. So here you see we have a bunch of components in our series all raised to the n. So what I want to do is I want to rewrite this so that way I've got just one single term raised all to the n. So we're going to separate the 2 from the n. So what we're going to have now is e squared over n, all raised to the n. So this stuff is clearly positive. So I don't need to worry about, if I take the absolute value, it's just going to return the stuff inside. So if we perform the test, what it says is we want to take the limit as n goes to infinity of the nth root of this. In terms of exponents, we can always write radicals as fractional exponents. So the reason this works out for us is what we're really saying is take all that stuff to the n and then raise it to the 1 over n, right? So if that were the cube root, we would have said 1/3, but this will always be the nth root. So clearly n times 1 over n is 1, so the nth root just wipes out the exponent. So now we just have to evaluate the limit of e squared over n. So what is that going to be? 0, right? You have a constant on top, n on the denominator, so you have a constant over infinity. This is 0. That is definitely less than 1. So we can say that this series converges absolutely. So I gave the handout out last week of the guidelines and how to do that. I don't think I brought them with me today. So they're going up on ELC right after class. So if you didn't get one, you can print them off there. I will bring some tomorrow to class with your quizzes, so I can definitely give you some more there. But that's the end of this section. This is a very straightforward test. You always want to just look for lots of elements raised to the n, and even if it's alternating, right, when you take the absolute value, that's going to wipe out all the alternating terms. So one of the mistakes I've been seeing a lot of people make is when they try to apply this test, under the radical, they'll have like -1 to the n, and then they try to remember we can't take the square root of a negative number, but in this case, you can't have anything negative because n could be any value, right? We can't have anything negative under here because all of the even terms, when n is even, it would violate that, and so we're taking the absolute value first anyway. So the absolute value is going to wipe that stuff out. So that's the end of this section.